Number 6 on the 1998 practice ACS. So number 6 says which best represents the ground state HOMO for a butadiene. So remember, HOMO stands for highest occupied molecular orbital, right? HOMO stands for highest occupied molecular orbital. So basically what you have here is a butadiene. All right, so there's that picture of the butadiene. That's butadiene. 4 carbons, diene. What they want to see is how would the actual molecular orbitals look, right? So we have 4 p orbitals here, right? And remember, we've been talking a lot about resonance, right? We can move, right? These electrons can be moved pretty much all throughout these 4 carbons, right? So what's the lowest energy state? If I have 4 p orbitals, what's the lowest way I can line them up? Like would be the lowest energy, would be the most bonding. What would I have to do? So if I'm going to draw 4 p orbitals, because right, we have how many electrons are in this whole system? How many electrons in the pi system total? In the pi system, how many are in there? 4. Take a look, right? 1 pi bond, 2 pi bonds, right? There's 4 electrons total spread out. So it's 4 electrons total spread out over 4 p orbitals. So if I want to get these 4 electrons, right? There's 4 p orbitals. How could I make them so they bond the most? How would I do my shading? All the same, right? I'd want the shading to be, right? Everybody be, right? Exactly the same. That would be, right? That would be the best, right? The electrons be the most positive interaction, most constructive interaction, right? Now let's go up one level. Let's draw 4 more p orbitals. That would be the lowest, right? Everybody has the same shade, so it's the most constructive interaction, right? All these orbitals are the same shade, like waves, right? So these are all going to be constructive interactions. Yep?
But wouldn't there be, I mean, like, because you're assuming that the electrons are in the dark area, right?
Nope. Remember, don't. Remember, electrons are waves. They can be above the crest or below the crest. The shading has nothing to do with where the electrons are at. That just has to do with what is it, a wave, a positive or a negative wave?
So if it's a positive wave, then they're all right next to each other.
No. So remember this. So if I have a wave, right, and this is the baseline of the wave can be above the water and it's also below the water, right? But if 2 waves come together, right, so imagine the top here being the shaded. So a wave like this, if these 2 waves come together, right, these 2 waves combine, what's going to happen? They're going to make a bigger wave up and a bigger wave down. That's what this is. Imagine above the water is the shaded part, and those 2 shaded parts are interacting. Below the water, right, those 2 parts are interacting. Right, so that's the lowest energy possible. And that's still bonding, right? We're all bonding. Remember we talked about bonding, right? Have to have orbital overlap and the right shading. So that's all bonding. That's the lowest one. Yep?
When you say lowest energy possible, are you, because what I'm thinking is electrons are all at the bottom, right?
So now be careful, right? So the electrons aren't. The electrons are being spread out through here.
And if they're being spread out on the same side.
Nope, they're spread out. They're everywhere.
Everywhere?
They're everywhere. Top, bottom. They're being shared equally, right? This is the best way to share them. Right? We're sharing them the most efficiently this way. Right? So think of it that way. It's the lowest energy because this is the best interaction we can possibly have with these 4 combinations. So what's the next best? So we can't be better. This is the best. This is the best way to share electrons. This is the best way to get things overlapped. What's one step up would be, well, one step higher in energy would be these 2 guys bonding. That's perfect. But then these two p orbitals are bonding over here, but right here, that's a no. Right, there's no sharing of electrons between there. So this is still bonding, right? Still bonding best. Bonding right between electrons, not as good, but still good. Right?
Wait, so that is the one on the left.
Well, yeah, so when I initially drew this, this looks just like this, right? This is also the lowest energy too, best orbital overlap. This is the second best. And remember, in an orbital, in a bond, right, we call these molecular orbitals, how many electrons in a bond? Two, right? So there's 2 electrons in this guy. And there's also 2 electrons being shared between these guys, right? Because we had how many electrons total did we have initially? 4, right, electrons in the pi system, right? So think about it. 2 electrons are being shared in a great way. The other 2 electrons are being shared, right, with the pi bonds. Let me redraw it for you to make sure you remember what it looks like. So 1, 2, 3, 4. So this orbital, molecular orbital right here represents, right, if this is 1 and 2, this is that pi bond. And 3 and 4 represents by this pi bond. Because do we consider there to be a pi bond between 2 and 3? It's not a full pi bond for sure, right?
Kind of there.
But it's kind of there, right, because of resonance structures, right? We can move these electrons around. So there's kind of a pi bond there, but not all the way. And that's what this is kind of representing. You see that? Because it's spread out. So now back to highest occupied molecular orbital. So which one actually still has electrons? This one has electrons still. Right? Because how many electrons total did I have? 4. How many electrons in a bond? 2. Right? We fill orbitals, bonds, 2 each. So this is the answer, which would be, let's see, is it A? So the answer should be A. 6. The answer is A. So another way to think about this, right, is to say, okay, how many, we've agreed, everybody's agreed hopefully, we have 2 pi bonds, right? 2 pi bonds, which is represented by how many p orbitals? How many p orbitals for those 2 pi bonds? 4. 1, 2, 3, 4, right? How many electrons is in that pi bond system? 4. So what we need to do is figure out how many different ways can we organize these p orbitals. What are the ways we can organize them? Right? So if there's 4 p orbitals, how many molecular orbitals can we have? 4. Right? 4 orbitals in, 4 atomic orbitals in, 4 molecular orbitals out. Right? We did that with hybridization. So if we have, right, what are the possibilities? So I could put them all the same shade, right, like this, and that would be good. That's constructive, right? They're overlapping. I could put these 2 overlapping, make a break here, make these 2 overlap, but not these middle 2. And then what would be another configuration I could do?
Like none of them overlap.
What's the next lowest
Oh, just the 2 middle ones.
one? Let's see if I can shrink. Maybe I'll retry this. So I can put all 4 in the same shade, right? And that means everybody's happy. Everybody's overlapping. Right? That would be the lowest energy, right? So think of it this way. We had 4 pi electrons. Right? That's what we started with. 4 pi electrons. We could put it so just these 2 and these 2 overlap, right? And then there wouldn't be an interaction here, right? So that would be a little higher in energy. That wouldn't be as much bonding, right? Now I could go up here and I could say, well, now these guys aren't going to interact. in either of those. So there'd now be a break here. All right, there'd be a break there. But now, look it. There's a little bit of bonding there. And then the last one would be what? All bad, right? I can draw it over here. Right, that'd be all bad. So there'd be break there, a node there, right? So what we call these breaks nodes, right? That's where electrons are not at, right? So if you have more nodes than bonding interactions, are you a bonding orbital or an antibonding orbital? Antibonding, right? So we call this, right? This we call the highest occupied molecular orbital because, right, if I take these 4 electrons over here, and I have to fill my orbitals, right, because I always fill the lowest energy ones first, right? So I put 2 electrons here, I put 2 electrons here, right? But I'm out of electrons for these guys. So the highest occupied molecular orbital looks like this, and the lowest unoccupied molecular orbital looks like this. That's the one where it's first, you don't have as much bonding as you do non-bonding. Couple things to make sure you hit on. So why is this? This is over. There is a bonding interaction here. Definitely a bonding interaction. But there's a non-bonding and a non-bonding. There's more non-bonding than bonding. So this is actually a antibonding orbital. We would call it pi star. Remember? If you put electrons in pi star, what happens? You break the pi bond. Then this HOMO is actually the pi bond. Right?
Why is that better than the lowest? Oh, because it's the highest energy occupied.
Yes, so right, let's look at our definitions, right? So we had 4 electrons to start. We took 4 p orbitals, right? We took 4 p orbitals, and we're going to combine them to form molecular orbitals. So if we start off with 4 p orbitals, how many molecular orbitals must we end up with? 4. 4 go in, 4 come out, right? Remember we did hybridization, it's the same idea. We took s and 3 p's and made 4 sp3s. You took 4 atomic orbitals and made 4 molecular orbitals. So same idea here. We're taking 4 p orbitals and we're going to make 4 molecular orbitals. All right? We have 4 electrons. We find the combinations, right, where this has 1, 2, 3 bonding interactions. So that's the lowest energy we can put. So we put 2 electrons in that because we fill orbitals lowest at a time, and 2 electrons per orbital. The next one we have 1, 2 bonding and 1 non-bonding, but that's still bonding. So we put the next 2 electrons in there, right? Because how many electrons do you put in an orbital? 2. And that's called the highest occupied, still with electrons, but the highest energy occupied molecular orbital. 1 up, we have 2 non-bonding, and then 1 bonding, but it's overall non-bonding, so we call that the lowest, right? And lowest meaning lowest energy unoccupied, right? We don't have, right? How many electrons do we start off with? 4. So how many can we totally have in the end? 4, and we always go bottom up, right? With lowest energy first. So this is called the LUMO, the lowest unoccupied molecular orbital. Or we also used to call that pi star. So to be really clear here, this doesn't mean there's 3 bonds here. This means there's 3 bonding interactions, not 3 bonds, right? At the end of the day, we still, right, what's the molecule originally? It's still butadiene. We still have 2 pi bonds, right? This is just helping us explain those 2 pi bonds a little bit. We still only have 2 pi bonds, but we have 3 bonding interactions here and 2 here. So it's a little different bonding interactions, right? Orbitals overlapping, not necessarily representing bonds. It's still only 2 pi bonds here. It's just how these electrons are being shared, right? How to think about where they're at. The most important parts are always the LUMO and the HOMO, right? Because this is always, right? Guess what the HOMOs are always? The nucleophiles, right? And the LUMOs are always the electrophiles, right? Pi and pi star. So how about number 13? What would be the relative rate of hydrolysis of these compounds in water and acetone at 25 degrees? So if we take a look at all of these compounds, what kind of alkyl halides are all of them? Tertiary. Do they have the same alkyl halide too? They're all chlorine too, right? So the leaving group's not changing. They're all tertiary. So if something's tertiary, right, and they're talking about hydrolysis, what does hydrolysis mean? Right? If you hydrolyze something, you've added water, right? Hydrolyze. So they're talking about hydrolysis. So this is going to be a substitution. You're adding water. You're switching water for the chlorine. So this is a substitution question. And they also drew this like this, right? So they're testing you a couple different ways here. Do you know what this means? Do you know that this is equal to that? So this was Roman numeral 1. This is Roman numeral 2. This is Roman numeral 3. So this is a substitution reaction. Everybody agree with that? What kind of alkyl halides are all these? Tertiary. So what kind of substitution reaction must it be? So it has to be SN1, right? It has to be. It's tertiary. Can we do SN2s on tertiary alkyl halides? No, right? So we have tertiary alkyl halide. We know it's SN1. Good. So which one? So what's the question we got to ask ourselves here? So they're talking about the rate. Which one's going to go the fastest? Most stable intermediate. Excellent. Which one's going to have the most stable intermediate? 1, 2, or 3? 2. Why? So it's right. There's that. They're both benzylic, and you get that much more what? Resonance. So I would say 2 is going to be the best, and then probably what? What's the next best? 1, and then 3. And now we go look at the answers. Because I haven't looked at the answers yet, because that's a sure way to get confused. So is there one that says 2, 1, 3? That's B. And is that the right answer? Excellent. Right? So what are they looking for? Terms, hydrolysis, adding water, recognizing that they're tertiary alkyl halides, and they're all the same, right? They're all chlorines. And then thinking about what's the stability of intermediate, right? Which one's going to be more stable? That's going to make it react faster, right? So be looking for things like this, right? Oh, there's 2 benzene rings, right? If you had no idea, right? Okay, strategy time. You saw this, and you're like, oh my God, I have no idea, right? Ooh, no idea. But you should look at the 3 things and say, well, what do they have in common? What do they have different? What are they different? Well, this one has no benzene rings, and this one has 2, and this one has 1. Well, if I'm going to rank these, I would either do one way or the other. You have 2 options. Either put this one or put this one. Because, right, this is the middle ground between these 2. So you have basically, you have a 50-50 shot without knowing a clue, right? And if you had even a better clue, you say, well, I don't know, there's 2 benzene rings. That seems right. And I think he said something about benzylic position a lot. He was always talking about that. Maybe I'll put 2, 1 then. Maybe 2 is the fastest one, right? And you can have no idea, right? You just looked at these 3 things and said, well, okay, there's those 3 things. Either this is first or this is first. This has benzylic stuff, so I'll put that one. And this is the next most like it, so that'd be 2 and this would be 3. Without even reading the question, I could rank it like that. Right? Let's look at number 11. And this one's asking us to rank the strongest acid to the weakest acid. So again, you're not gonna be surprised here, but a lot of these questions on this test are gonna have a lot to do with resonance. So these all have phenyl rings. Oops, I drew that one wrong. That's the first mistake. This is a benzyl alcohol. This is a phenol. Number 11, my bad.
That's what you meant, right?
That's what I meant.
Yeah.
So now, which of these is going to be the strongest acid? Right, so remember ranking questions, what's the strategy we try to do? Find the worst and the best, right? Find the polar ends, right? That helps us do this, right? Find the ends. So what are we asking ourselves here? What's an acid? What do acids do? They donate hydrogens. Acids donate hydrogens. So we're probably talking about that H, that H, that H, and that H. Now, for a reaction to take place, one of two things needs to happen. You have reactive starting materials, or you make stable products. What kind of things make products stable? Resonance. So the more resonance you have, the more stable you are. Very good. Okay. Which one of these is going to have the most resonance once this becomes O minus? Which one's going to have the most? Oh, let me number them. 1, 2, 3, and 4. Which one's going to have the most resonance once we have O minus? 4. Absolutely. So 4 is our highest ranked one. Right? Which one is going to have the least amount of resonance, or maybe even no resonance? 1. Here's the trick. This is what they're trying to get you. That's what's the hybridization say of that carbon right there? sp3. Can it do resonance? No. Whereas this one, this O minus is right next to the benzene ring, so it can do resonance. That's the trick they were trying to show. Did you understand that you can't do resonance here? So the worst one is 1, and now we got to decide between 2 and 3. Well, I don't know about you guys. What kind of functional group does number 2 have?
Carboxylic base.
Carboxylic, the old carboxylic base, of course. No, right? It's carboxylic acid, right? But remember, be careful though, because remember, a carboxylic acid is not more acidic than this. Right? This is like sulfuric acid. Remember H2SO4? This has even more resonance than the carboxylic acid one. Right? Carboxylic acids are acids, but are they strong acids? No, they're not. They're not reactive acids, right? They're still there. They're good, but they're not the best. So 2 and 3, and everybody sees that 3, right? 3 can do resonance within the ring, but it's not the best way because you have to break up aromaticity, right? Whereas a carboxylic acid doesn't have to break aromaticity to do some resonance. Good. Does that make sense? So let's look at number 55. All right. In which reaction is an organic compound oxidized? Very good. So remember, this is a good kind of definition question. Do you remember what an oxidation is? What happens in an oxidation? Lots of electrons. And in organic chemistry, we've talked about give me an example of an oxidation that we've done in this class. What have we oxidized? That's the reagent, but what have we oxidized? Alcohols to ketones, aldehydes, carboxylic acids, right? We've turned alcohols into carbonyls, right? We've removed H's. So when we see oxidized, we should be thinking about that. So which reaction is an organic compound oxidized? So A just looks like an SN2 reaction, right? So A is an SN2, right? There's a new bond to carbon with oxygen, but there's no H has been removed, right? No electrons have been removed. B is a reduction, right? B is actually adding H's, so that's a reduction. C, what's C? C is just an SN2 as well, right? C is an SN2, or actually not an SN2, it's a Fischer esterification. Good. The Fischer esterification, that's like the banana oil lab we did. That leaves D, which shows this alcohol. And you see, by God, you see chromium there, right? That should tip you guys off. Cr2O7, right? Anytime you see that chromium, and we took an alcohol and turned it into a carbonyl. So oxidations, right? For us, we've talked a lot about, anytime we turn an alcohol into a carbonyl, that's been an oxidation, right? We've effectively removed that alpha CH, right? That's the oxidation we've been working on. Good. Number 35 goes over a Diels-Alder, which is a super complicated reaction, but one of the classics in organic that forms 6-membered rings. So the way this works, it says, what is the product of the Diels-Alder reaction? So the way you need to look at this is you need to get So if I redrew this, right, you have these two things, and they're asking, right, we're going to heat it up a little bit, what does it make? So two things you need to do for a Diels-Alder reaction, or one thing you need to do in the Diels-Alder reaction. When we have this diene, the diene part, you need to get this in a different conformation. So what that means is you need to rotate about this bond. So if we do a little rotation, it's not hard, this is not crazy here. You make it look like this. So it needs to look like that. All right? So it needs to look like that. So first thing you need to do is get it, the butadienes to be like this. Look like a little, what do you think?
Kind of looks like when we clicked in like the osmium.
Looks like a bug.
Yeah, it kind of looks like, yeah, you get that double bonds on the same side, right? So it would probably be like the less stable version, right? They'd rather be away from each other. It's like getting things kind of, you want to get the two pi bonds on the same side next to each other. Okay. Now, we're going to number our carbons, 1, 2, 3, 4. The butadiene part has 4, right? Buta, 2 dienes. Then we'll say 5 and 6. All right? So carbon 5 has what? The 2 nitriles, right? And 2 has the O methyl, and so does 3. So the next thing you do is you draw a 6-membered ring. You put a pi bond between 2 and 3. So you have 1, 2, 3, 4, 5, 6. So you form a new bond between 1 and 2 and 3 and 4. And you form a pi bond between 2 and 3. That's what you do. So just do that automatically. And then you need to fill in what's still there. That's still there. This is still there. And where are the 2 nitriles at? Which carbon are the 2 nitriles on? They're on 5. So you put the 2 nitriles there. So if I drew the arrows to show you, it's a lot like, it is a lot like the osmium one actually. All right, these electrons would go there, these would go there, and these would go there. All right, so you form 3 bonds, 2 sigma bonds, right? 2 sigma bonds between 1 and 6. Sorry, I said that wrong before. Between 1 and 6, 4 and 5, and a new pi bond between 2 and 3. The tricks, got to get it in this conformation with the 2 pi bonds, the diene part on the same side. Number your carbons just like this. Right? The alkene part, just make sure if there's 2 nitriles on this, they stay on that same carbon. They're not going anywhere. Yes? Let me throw an extra wrinkle in here. It's not hard, I promise. I'll take the same, mostly the same example, the same diene. I'm going to change the alkene part. I'm going to put these 2 nitriles. Those 2 nitriles are what to each other? Cis or trans? Trans. So in the final product, should they be cis or trans to each other? So let's think about what's that going to look like. So we number our carbons. 1, 2, 3, 4, 5, 6. We move our electrons. We draw a 6-membered ring. Pi bond there. O. So how am I going to represent that those nitriles are on different sides? What am I going to have to use? Wedges and hatches. Does it matter which one I do? Nope. As long as they're opposite, it doesn't even matter. So as long as, right, if this is this way, if that nitrile is wedged, then the other one has to be hatched. Because if they're trans in the beginning, they need to be trans in the product. So what if they were both cis? If they were cis to each other, then they'd have to be either both wedged or both hatched. Either one's right. So be ready for either one, right? You know, renumber these carbons. 1, 2, 3, 4, 5, 6. Does that make sense, everybody? right? That's the quick and dirty way of, it gets a lot more complicated by all means. But the trick is, the two tricks, got to get the diene, the 2 double bond part, into this conformation. Number your carbons. They always make a 6-membered ring with a pi bond, right? And then on the alkene part, if these nitriles or whatever's off them, if they're trans, they need to be trans in the product. If they're cis, they need to be cis in the product. And we could have drawn this another way, right? Everybody understand that? We could have drawn this with a wedge and this with a hatch, right? So maybe the answers, they might not give you exactly the answer you drew, but it could be the enantiomer of it, right?
Oh, that's not fair.
Good? Yeah, so finally, what's the correct answer for 35 then? Let's just, D. So the correct answer was D. This is D, so good. But yes, these will show up. I'm going to say this on video too, right? Take a look at this. Understand this, right? There'll probably be 1 or 2 questions on the test on this. Right? 33, which is asking, which ion is generated as an intermediate in the formation of the major product in the reaction of toluene with SO3 H2SO4? Electrophilic aromatic substitution, right? So do you know what toluene is? You should. That one we know. So this is toluene, right? That's toluene. Toluene has a methyl group on it. Is that an activator or deactivator? It's an activator. Where do activators direct? Or, yeah, so it pushes electrons in, right, because of hyperconjugation. So we know this is an activator, and we know it directs ortho and para. Right off the bat, you should write that down before you even look at the answers. So now we say I'm either gonna put the SO3 where? I'm either gonna put it, the SO3 either goes here, para, or it goes to one of these ortho spots. Right, that's where it has to be. Right? So now I can look at these and say, wait a second, which ones can I eliminate right off the bat? You should be able to look at these answers and you should be able to eliminate A off the bat. A is not ortho. And C is meta. So now you have between B and D. So let's just draw this. And B and D both have what? B and D both have the thing on para, right? So if I have an electrophile, it doesn't matter what it is, and I put it para, where's the plus charge going to end up? Everybody see this? There'd be a plus charge on the meta position, right? Right? Why? Meta to the methyl of the toluene, sorry. Or right next to the electrophile, there'd be a plus charge, right? Anytime there'd be if the electrophile adds, the plus charge would be right next to it, right? So which one is that? That is B, right? So B has that. D had the plus charge. D had the plus charge. And the ortho spot, but that you'll never get that if you've added the electrophile para. You'll never actually get that. Let me clear that up a little bit, sorry. Right? The plus charge will always be right next to where the electrophile added. So that's B. So worst case scenario though, worst case scenario again, you knew this and you had a 50-50 shot to get it right, which is twice as good as 25%.
That's true.
All right, so let's look at number 65. This gives you an IR and an NMR. So what we look at this, we'll say, from the IR, what can we tell? From the IR, and you will not be giving your sheets, but you should be able to look at this and say, from the IR, what do I have? So if I look at the IR, I have a peak in the CH region, which is around 3,000, right? The CH region, we talked about the SP3, SP2, and SPCHs, right? Looks like I have a CH and SP3CH, that's below 3,000. If I look at that, that's below 3,000. So I would write SP3CHs. I don't have any SP2 or SPCHs because there's nothing beyond 3,000. So you should know those three things, right? SP3 is below 3,000. SP2 and SP are beyond 3,000. You should know that. And higher numbers. Beyond. Higher numbers. SP2 and SPCHs are higher than 3,000 wave numbers. You also see a peak at So this is at about 2950. You also see a peak at 2270. Right? That is your triple bond region. But I can't have a terminal alkyne, but I should be thinking maybe nitrile or maybe alkyne, but one of the two, right? That's a triple bond region. Around 2200 is a triple bond region. Right? Also, I have a peak at 1745. And that should tell me what? That should be C double bond O. And maybe you know exactly what that means, Esther, maybe you don't. But you should know it means carbonyl. Right? Fair? Okay. Now, what does the H NMR tell us? Well, so they didn't do us a favor here, and they didn't tell us exactly how much those H's are worth. Right? They did not, that's too bad. But you should see, if I looked at this, if I draw this out for us. This is at 4.1, this is at 3.5, and then there's a triplet at 1.4. So they didn't tell us this is worth 2 H's, this is worth 2, and this is worth 3. Now they didn't tell us that, but the integrations, I mean, you can kind of see from the integrations, right, the little curved line, the one to the far right is bigger, right? So that what I mean by that is if this is this big, this should be exactly the same there, and then this one should be just a little bit bigger, right? A third bigger. So if you see this, I see this is a CH2, right? It's worth 2 hydrogens. So I would draw a CH,
How do you mean that?
because I looked at the curves. They gave us the curves, and you got to look at the curves and assume how much they're worth. And guess. The one at 4.1 is worth 2. This one, oh, maybe I do have it wrong. My bad. See? Actually, this one should be worth 3, and this one should be worth 3 as well, I believe. No, that's 2. No, I had it right before, guys. I had it right before. If you look at the peak in the NMR, right? Look at the size of this. This is not given to you, but look at the size of this. Right? Look at the size of these peaks. If it really comes down to it, my personal opinion, it's not fair, and I'll tell you the relative ratio. Honest to God, if we get to the test and we have something like this, I will tell you the relative ratio because, in my opinion, that's ridiculous that they just don't give it to you. I will tell you the ratio. So let's just assume you knew 2, 2, 3. Fair? Because that's silly. That's absolute nonsense. No, you shouldn't. Yeah, maybe this was made in 1998, and no, I will tell you the number. I will tell you the number. Fair enough?
Yeah.
I promise I'll tell you. Okay. So that means if this is A, this is B, and this is C. So A is split into a quartet. How many nearest neighbors does A have? Has to have 3. And notice where A is at. Where is A at? What frequency? So it's probably bonded to what? An electronegative thing. And if you look down here, it's probably bonded to, right? I don't know, an oxygen, right? That makes sense. And then you have a peak at 3.5 that is a CH2. And how many nearest neighbors does that CH2 have? How many nearest neighbors does it have? It's a singlet, so it has none, right? But it's pretty de-shielded, right? It's at 3.5. This is B. And then this is obviously over here, this would be C, right? So now we go to our answers and say, well, which one of these have it set up that works? So let's look at A. What does A have? A has a nitrogen and NH2. Is there any NH2 in our IR? No. Right, so it can't be A. Yes? So we look at C. C has 3 different types of, right, has 3 different types of H's. But that peak on the far left, that CH3, that would be, how many nearest neighbors does that have? If I draw these out, here, I'll shrink this up quick. The last thing we'll do, I promise. right? If this is C, right, this would have how many nearest neighbors? Or how many peaks would it have? How many different types of hydrogens does it have? It has A, B, and C. But A would be a singlet, right? How many H's would it be worth?
3.
Do I have a singlet worth 3 H's? No. So can it be C? No. If I look at D, D is D is the next best answer, but D is confusing. But if you remember, if you need to be bonded to an oxygen to be really de-shielded, right, is this CH2 right here going to be de-shielded enough
No.
to be at 4.1? No. So it's not D either. The answer in this one is A. Make sure you take a look at it and go back. But these are tough ones, right? These are ones, right? They're going to take some time.
Whoa. Whoa.
The answer is B. That's darn
You
it.
said
Sorry.
You can't have A 'cause there's no
They can't have A because there's no NH2 in the IR, right? Sorry. It is B. The answer is B. But you got to do a process of elimination. These are tough ones. They'll take some time. So, feel free to skip questions and move on. All right? I will record this one, and then you'll have the other one from the other class.